Okay, just doing an audio and video check. I'm going to go to questions, lectures. Just to do an audio check on YouTube. Someone give me a thumbs up on the questions, lectures channel that we're all, audio's good. Wonderful, thanks Harley. And just checking that you can see the Monday week 12. Awesome. No title page. Ah, that's right. Thank you. Okay, thanks. I'm just going to go into a little bit of testing with Brenton. So I'm going to, you might see a bit of testing going on, but that's fine. We'll lecture to commence at 9:05. Wonderful, thanks. I'm going to do a little bit of testing with Brenton, so you might see a bit of stuff going on.
Yeah, I'm here, Steve.
Oh, wonderful, Brenton. That's great. I think I've set things up so that you're able to share your screen. I've had a couple of other settings that I've needed to do a little differently, but you should be able to.
Yep, I've got the button, and if I click it, it just brings up a warning that it's going to stop your screen share. Do you want me to just do that now?
Give it a go. We're 3 or 4 minutes away from switching to the class. Looks good to me.
There we go. Cool. I haven't got the camera on, but this will do.
No, that's fine. That's great. Looks great. Wonderful.
We'll see how the demo goes. Doing it from scratch is slightly different from what I'm going to demonstrate, but
look, you know my view on everything. If it's 80% right, it's right.
Look, it's not possible to give a demonstration that's going to suit everyone.
No,
there's little things like whether Git is installed or exactly what dialog pops up or whether you've logged into GitHub before. Yeah, there's
got it.
The only way to do it from scratch is to just spool up a completely blank VM and just do it from scratch and hope that whoever's following it has never done any of this. Yeah. Just
not in week 12.
If you're doing it yourself, you just got to work it out.
Exactly, 80%. Yeah. No, that's beaut. I think it's so much more powerful than just an abstract list of concepts.
No. Anyway, look, the PyCharm Git integration looks okay.
Yeah, good. That's good.
So
that's good. I'll be curious to see how that goes.
Yep. Anyway, I'll wing that whenever. Are you going to be doing C or Git first? Like when do you want
C first, and then the last few slides of my presentation are Git, and then there's a handover to you right at the end.
Okay, cool. Well, I'll be here.
Wonderful.
I'll just watch and be ready to go whenever.
Awesome. Thank you. You might like the final slide in my slides. Okay, welcome to the Monday Week 12 lecture. I've just done a little bit of testing with Brenton, so if you can let me know, I'll assume that all is good with audio and video and that we've handed back to me. Let me know in the questions lectures channel if there are any problems either hearing me or seeing the title page slide. So here we are in week 12. Really our final content lecture as such today. I'll say a little bit more about Thursday towards the end, but this is really the final content. And in saying that, Brenton and I are jointly going to present some material today on the C programming language, and then something known as a version control system known as Git. And neither of those are actually accessible in, oh, thanks. Make sure I go back, just give me a moment. Just give me a second, I've got to share my screen again. More to the point, got to work out how to do that. So I think I've got the title page displayed. Someone can let me know. Wonderful, thanks very much. Okay, so let me just back up. So Brenton and I are doing a bit of a joint presentation this morning. So we've had a couple of little wrinkles with screen sharing and such. So two bits of content today. It's our final content lecture. I'm going to give you an overview of the C programming language, and then we're going to introduce a few of the principles and a little of the practice of something called a version control system known as Git. So towards the end of my presentation today, I'll hand over to Brenton and he'll give you a run through of what Git looks like in practice. So to be clear, neither of the pieces of content that we're presenting to you today will be in the final exam, full stop, no question about that. That doesn't mean it's not important, because I think both the content pieces that we're looking at today, both the C programming language and version control, are very important, but they're more important as you look forwards in your study program as engineers and IT professionals, rather than something that's going to be assessed in the exam. So a little bit of backup, we'll look at content, the context of the ENGG1003 course as it is now, and how it was up until including last year, wherein the C language was taught. So that begs the question, do we even need C? And somewhat similar to my response on the use of MATLAB that we looked at last Thursday, my answer is, do we even need C? Yes and no. Let me be clear, C is not accessible in the ENGG1003 course this year. It doesn't mean that you won't need it in later parts of your study. And I want to make some linkages that are useful for both the students among you that will go on and use C. I'll give you some of the idea of why you might use C and not Python in later courses. But for those of you that don't need C later in your program, I still want to give you some value in understanding what the C language is about and how it fits into the global picture of programming languages. So I'll talk a little bit about the features and philosophy of the C programming language. And rather than do what I did last week in MATLAB and present some MATLAB Python comparisons, I'm going to give you a sense of what the C language is like by giving you several small sample programs through which you'll both see some similarities with Python, but also some really key differences. And then towards the end of my presentation today, I'll talk a little bit about the principles of something called version control. We'll talk about the motivation for why and why you might need version control. and then just a bare bones principles of something called Git, a version control system. And then I'm going to hand over to Brenton, who's going to give a live demonstration of Git. So with that as background, let's get into the context. So I'm going to follow a little bit of a pattern that I followed in last Thursday's lecture. You'll probably recall that up until and including last year, the ENGG1003 course used two programming languages, one of which was MATLAB and one of which was C, and roughly midstream changed from, I think it was C taught first, and then the back half was MATLAB. This year and going forwards, this course is using Python only. So to be absolutely clear, C is not accessible in the ENGG1003 course this year. Yet some of you will use MATLAB and some of you will use MATLAB and C in later courses. And so where we, on Thursday of last week, I gave you an overview of MATLAB and made the claim that should you need MATLAB in a later course, I reckon any student that's passed this course could make that transition in no more than 2 weeks, and probably a lot faster than that. Today's lecture, I'm going to give you an overview of C, and the message is going to be different. I don't think it's possible to make it a completely thorough transition from Python to C in 2 weeks. C as a programming language has lots of little, is a powerful language, but it's also a subtle language. And the transition from Python to C, I would argue, is not completely straightforward. Doable, but doable in the context of follow-on courses where you see the C language used in context. So at a high level, C is a general purpose high-level programming language. I'll remind you what high-level programming language means in a slide or two. And there are many other general purpose high-level programming languages: Python, MATLAB, Java if you're doing saying 1110 and 1120, C++, Fortran, and the list goes on and on and on. I would argue, though, that among all those languages, those high-level languages, C stands alone. It has quite a unique position in programming languages. It's been around for 50 years. The first version of the C programming language appeared 50 years ago next year, and yet it's still very popular. The IEEE, which is a professional society of electrical engineers, have an annual computer programming language popularity ranking that they release. The #1 language there is Python, which is great for you. The #3 language on that list is the C programming language, and for context, MATLAB comes in at #10. C it really is in a unique position. It's the native language of almost all the operating systems that are in existence at the moment: Linux, Windows, Mac, all the iPads, iOS, iPhone, Android kernels, and on the list goes. Even the C programming language is written in C. Even the Python programming language is written in C. I've talked before about how I've mentioned much earlier in the course how Python's an interpreted language. That may or may not have made a lot of sense depending on what your experience with programming was. My goal today is to show you what a compiled language is about. Not the details, but the broad overview of what a compiled language is about. Python's not a compiled language. Python's an interpreted language. And actually, the language of Python itself is written in C. So when you type instructions into Python, the program that takes those instructions and does the stuff that you asked, that program is actually written in C. And the reason for that is that the C programming language takes its instructions and maps them to computer hardware, or so-called machine instructions, very efficiently. So a very uncharitable view of the C programming language is that it's a very efficient way of writing machine code. It's much more powerful than that, but that's one way of thinking about C. And I've got some examples later and some hands-on activities that'll sort of bring that to life, I hope. So the question is, do we even need C? Two-part answer. First part, it's not accessible in ENGG1003. There will be no C assessed in the final exam. However, many of you, depending on your programs, will go on to do courses that do use C. And if you're in the aerospace systems engineering, computer systems engineering, electrical, mechatronics, or medical engineering programs, you will take one or more courses, and I've listed 5 of them below. I think that's a comprehensive list. Don't quote me on it. It's a fairly comprehensive list. If you look ahead in your program and see any of the 5 courses I've listed there, you will come across, in fact, you'll not just come across, you will use C as an integral part of those courses. Now, the common theme of all those courses are embedded systems. So an embedded system is where you've got a really tight coupling of hardware and software, where you've got a microprocessor design that's operating to perform a very specific task. Our world these days is surrounded by embedded systems that we barely acknowledge exist. Your washing machine, for example, it's got inputs in the form of buttons and might measure a water temperature and a water level. It'll generate outputs, a simple display on the front panel. It'll send some control signals to a motor to control the speed of a motor. All of that under the control of a microprocessor with a small amount of memory. Really no large-scale operating system to speak of. The microprocessor that controls your washing machine probably costs $1 or less. It's got a very limited amount of memory. It's got a relatively slow clock speed. It's got a very specific task in life, and that is to control your washing machine. There's a myriad of other examples: smart TVs, gaming consoles, medical devices, Wi-Fi routers, automotive. If you've got a modern car, it's probably got dozens of microprocessors in it, all operating in an embedded environment. If you've got if you're controlling the rear view mirror on your cars, it's almost certainly in a modern car under the control of a microprocessor as part of an embedded system. It's hidden away. It does a very specific task. It doesn't require any large-scale computation. Doesn't need to run particularly quickly. But the point is that the software that controls that system is written very specifically for that particular task in mind. And the C programming language is very well suited to that very tight coupling of hardware and software. And in fact, in many of those embedded system courses that I've referred to there on page 5, the heart of those courses is hardware and software co-design. So you don't just you're not just given hardware and assume that it works and write high-level software for it. You're designing the hardware system that fits around the microprocessor at the same time as you're writing the software. So they're really tight coupling of hardware and software is what characterizes an embedded system. Let me just. So, and the C programming language is particularly well suited for that. And as I say, over the past 50 years, it's found itself almost in a unique position. To give you some idea of, I read a stat the other day. It actually related to 10 years ago, so I suspect the stat's even more true now. That something like 98% of the microprocessors that are manufactured these days, 98% of them go into embedded systems applications. They're worth $1. They control the rear view mirror on your car. And they've got these applications that mean the software needs to be making use of very little in the way of operating system commands and fancy output displays or fancy input displays. But the software that runs You need to know exactly how it's going to run on the hardware in question. So what do I mean by a high-level language? In order to talk about what a high-level language is, it's actually easier to talk about what low-level languages are, and then the high-level languages fit on top of those. So this is a computer language hierarchy that I did touch on briefly way back in week 1. When all said and done, microprocessors can only understand machine code, which is a binary code that's down at the instruction level. You get one instruction at a time, and those instructions are by definition only relevant to a particular microprocessor or a particular family of microprocessors. So that, what is it, 32-bit string that you see on the screen there at the top of page 7, that is in fact the instruction for an x86 based microprocessor and an Intel based microprocessor. Looking at that string, only a machine would know what that string meant. So it's not possible for humans to program, or at least not very efficiently, in this machine code. It's literally binary numbers that are stored in computer memory and interpreted by microprocessors. One level up from that is what's known as assembly language, and that's where the machine instructions are given human readable abbreviations. They're called mnemonics, and so that 32-bit binary string is actually an assembly language instruction that has this form down at the bottom of the page. Now, even if you've never encountered x86 based assembly language before, you can read that and know that it's got something to do with addition. And in fact, what that instruction does is take a particular register in a microprocessor, add the number 10 to it, and then put that number back in the register or memory location, a specific memory location inside a microprocessor. Again, it's very processor specific, which is important because ultimately machine code needs to run on a particular microprocessor. But for humans to either work in machine code or assembly language is either impossible or impossibly slow and inefficient. High-level languages like C and Python and MATLAB go one step further, and they are written in such a way that it's not only is the text-based code, the computer program or the script, human readable, it's human writable. And so it needs to be understandable by humans to the point where you can write a program in it. And so here we have the hierarchy again. We've got a 32-bit binary string. We've got the equivalent instruction in assembly language. And now we've got the same instruction in the C programming language, which is x is equal to x plus 10. Well, that's one interpretation of it, where we've got a human readable variable x. And I would go one step further and, it might be, rather than using x, if I was writing a C program or indeed a Python program, I would be writing not x, but water level or altitude of plane or light intensity, so that you've got a very strongly human readable and interpretable computer program, which is ultimately translated into machine code. Now, that translation of a high-level language into a binary code that's executable by a microprocessor is done in multiple stages. And for the C programming language, a so-called compiled language, it takes the chain of steps shown at the bottom of slide 8 in order to do that translation. Now, there are subsequent courses in computer programming languages where you get, if you were to choose those courses, will need to do them, you would be stepped through those individual steps in detail. I'm just mentioning the names here for you now. At the start of that chain is high-level code in C, for example, and at the end is machine code. And there's the two key steps, as far as we're concerned in this lecture, are what's known as the compiler and the assembler. And the compiler takes your high-level C program and converts it into the assembly language. and then the assembler takes that assembly language and produces machine code using, there's an intermediate step called a linker, not relevant to us here. So the high level, the view from space is that the C source code is converted into assembly language, these sort of single instructions, and then that assembly language is converted into machine code. So what I'm going to do for you now is show you your first C program, and then I'm going to bring up a web page that I've got a link to in the next slide, which is going to show the translation of that high-level C code into assembly language. So it's traditional in computer programming courses that the first program that you write is called the Hello World program. And here it is. It's got 7 lines of source code on page 9. If you've never seen C before, you can look at that program and probably take a guess as to what's going on. If you look at it for a couple of minutes, you'll see some elements that you recognize from Python, but also some quite distinctly different elements. The key line here is line 5, which uses a printf statement, which prints the string hello world to the terminal. Printf is the equivalent of a print statement in Python. In line 1, we've got in this green font, we've got this include statement with something called stdio. The way that you read that standard IO, it's standard input output. You can think of that as like a Python import statement. Now, my point here is not to make you expert C programmers. That would take at least one course and probably years of study to become expert in C. But it's to give you confidence that if you've seen Python, you're proficient in Python, then you could make the transition to C in the context of the embedded systems courses that follow. On line 3, we see something that says int main. This is the main function in a program, literally called main. Every C program has one main function. The int here means that it returns an integer as its output. The print statement we've already talked about. Something we haven't talked about is what this \n means in the string here. That's the code for a new line. So it not only prints the string to the screen, but it actually drops the cursor down to the next line. Now you might think that's a very minor and obscure detail. Yeah, it sort of is. What it's also highlighting, though, is the C programming language. Part of the philosophy of it is that it does what you want, but it only does what you say. If you want to print a new line on the terminal, then you've got to tell the C programming language that you want that to happen. It's not going to magically happen. It's not going to happen by assumption as part of the printf, which is sort of what Python does. It sort of says, oh, I know you want to print a string. I'll print that for you, and I'll put a new line ready for the next time you want to do a print. The philosophy of C is different. It'll only do what you ask it to do. So if you want to print a new line, you've got to put a new line character in. And then this return statement, we've seen functions in Python. They also return things. In this case, it returns a 0 back to the operating system to say, all good, the program's operated correctly. And the final thing I'd draw your attention to is in C, the use of these curly parentheses to mark the begin and end of a block of code. They don't exist in Python. Python uses indentation to demarcate the beginning and end of blocks of code. C doesn't do that. You've got to do it explicitly with these parentheses. Now, I've used indentation here to capture the idea of the block of code. You're able to use indentation in C, but the language itself doesn't require it. Okay. Now, normally what you do in a first course on C is take the Hello World program, and you'd have to install an integrated development environment that included a compiler with links to the operating system to print numbers to the screen. That's all very complicated for this first very superficial look at the C programming language. So what I'm going to do instead, because my goal is not to really introduce in any systematic way the elements of the C programming language, as much as to give you just a taste of what C is like. What I'm using is an online browser-based in development environment that enables you to put a C program in and run it without any installation. So sorry, wrong one. What I've got on the left is my Hello World program, and what I've got on the right are the corresponding assembly language instructions that correspond to that program. So here is the code I've exactly cut and pasted into the browser. There's a list here. There's a link here in the lecture notes to this one. So here you can see the source code on the left. Hopefully that's big enough. I'll just make the font a little bigger. So hopefully you can see it. On the left, you've got the C source code, and on the right, you've got the program itself. And because this is online, let me show you what you can do. Is you can take your, let me see if I delete that code, the assembly language disappears. If I then take my Hello World program and I'm going to paste it in on the left, the corresponding assembly language instructions appear automatically for you. And so you're certainly not expected to know what these push, move, call, pop, return instructions mean, other than to acknowledge that they exist. So the way I've got this set up is that I've chosen a particular compiler, which is going to target the Intel 64-bit Intel 86 architecture for the microprocessors. But what I can also do is choose it by using this drop down. I can actually choose a different microprocessor. Maybe I want to choose something called an ARM microprocessor, and then it'll generate the assembly language for that. Notice the coding here is reflecting the printf statement in yellow maps to the yellow assembly language instructions, and the return statement in blue corresponds to this one down here in this in blue. And so this is a really nice, it's just a bit of, it's sort of fun in a way, but it's also quite powerful. You can choose different microprocessors. You can choose something called a MIPS, and it'll generate the code for that. Completely different assembly language instructions. You might choose an Arduino, and it'll produce the instructions for an Arduino. You might choose a Raspberry Pi, and it generates instructions, the assembly language instructions for that too. All the while, I've got the same high-level source code. So that's really powerful. Well, that's a powerful feature of the C programming language. It's a powerful feature of all compiled high-level languages, but it's a really nice little, this compiler explorer is a bit of fun. I think that it'll enable you to pop in different programs. I've got some other programs I'm going to show you in a moment. Let's choose one, and I'll cut and paste some different source code. Here it is, different assembly language instructions. Let's go back to the x86, this one. And so you can, it'll generate the assembly language instructions for you for a completely different program. So I think that's sort of a bit of fun and quite powerful at the same time. So if you want to experiment, the links here included at the bottom of page 10. So what's my point? My point is that if you write a program in C, the compiler will generate assembly language instructions for a particular hardware architecture that you've targeted. Here's a couple of other views of the C programming language. quote that says the C language combines all the power of assembly language with all the ease of use of assembly language. That's not a very flattering view of the C programming language. Not saying it's my view, but it points to the fact that the C language itself, you could argue, is not very friendly. It's certainly not very friendly for students who have never programmed before and who probably won't need much direct use of computer programming later. For those of you that are going to study embedded systems, C is imperative. But at that point, you're thinking hardware, software, you're down at the individual instruction level, and C is entirely appropriate for you. Here's another view. Believe it or not, this is actually an ad for a book. It's not someone being sarcastic with the view of putting people off C. Learn to think like the computer hates you, because it does. It's a view of computer programming that says if something's going to go wrong with your program, it will. I can see some of you struggling and enjoying some of the challenge of some of the more complicated parts of the assignment. C tends to bring out those aspects of programming which gets you to focus on what data type. Is it uint8? Is it uint16? Is it float64? Converting between those types. When you're trying to solve high-level program problems, sometimes those sort of aspects of a programming language can be frustrating. When you're programming, when you're writing for embedded systems, they're imperative. It's not good enough to think, that number's got enough bits of precision to store the number to do the calculations to the precision that I want. It's not enough to think, there's enough memory on board for my computer program to use that data structure with 64-bit floating point numbers, whatever they are. So I'm drawing the distinction here between Python, where you're trying to solve high-level problems. Maybe you're trying to write a bisection algorithm, versus writing an embedded systems program where you're down at understanding how fast the program runs, how many bytes of computer memory it occupies, what other hardware resources are available in order to implement your program. So I'm certainly not negative about C. I suspect Brenton and I have slight differences of opinion about the C programming language. That said, Brenton's got 20 years of experience at writing C, and you probably need a number of years of writing C before you're really proficient at it. So you might be thinking, thank goodness we dodged a bullet and we're learning to program in Python. And I would concur with that view. I don't think C is definitely not the best language to learn as your first computer programming language, but it might be a very good language for you to use as your second language, which some of you will do. So normally when we're writing C, we'd need to have an integrated development environment, which includes a compiler and an assembler and a conversion of assembly language into machine executable instructions, and then the execution wrapper that makes all that happen. Just for this introductory taste of C, I've got a link here to an online compiler tool that allows you to run C programs with no setup. And so there's a link here. I've got at the bottom of the page, and I'll bring it up here now. Hopefully you can see the details there. So what you have here on in the gray area is a window in which you can cut and paste code. In this case, it's the Hello World program. Let me make it exactly the Hello World program that we wrote before. I'm cutting and pasting from an editor on another screen. So when we run this program, what we see down the bottom of is the display of the Hello World message to the screen, and it's included the new line character, and it's the program's run correctly, and it's returned back to the console. Let's see what happens just for fun if we take the new line character out. We run it again. The program runs, but it doesn't put that additional space in. So let's see, the effect of that is to put the new line. Let's run it. It puts an additional space down the bottom. Now, for those of you that have ever programmed in C before, I think you'll agree that this web-based system is a very friendly way of getting started with C. I'm going to show you 3 programs now, just to give you a taste of what a C program would look like. Not to make you an expert. That's not even close to being true. I'm just giving you a flavor and bringing out some of the main points in the C programming language. So our first program, not the world's most exciting program, but it's going to read an integer from the terminal, and it's going to display that with a simple message back to the screen. So let's run it first, and then see. I'm going to cut and paste. I've got the code. I've pasted this code in Blackboard, the C code. I've pasted it in Blackboard, and also the lecture code channel in Discord. So you can do exactly what I'm doing. You can cut and paste that code into the window. And so now so here it is. We're going to enter an integer. We're going to read it and then display it. So we run it. Down the bottom, it says enter an integer, 4, and the program says you entered 4. So it's not the world's most exciting program, but let's have a look at the details of it. So all I'm doing here is I'm picking out a couple of key differences between Python and C. One key difference is in line 3, where before we use a variable in C, we have to do something called declare it, which is our way of telling the compiler we want to use a variable, in this case called number, and it's of type int. So that tells the compiler that such a variable exists, and it sets aside some memory locations in computer memory to store that number. Here's the printf statement, which says enter an integer. No real surprises there. We've seen it before. Notice how statements in C finish with a semicolon. That's the way of telling the compiler that that particular C instruction is finished and that the next instruction will follow. Line 7, // is another way of using comments and providing comments that are not interpreted by the C compiler, but are there for human readability. The scanf function is an input function which reads a quantity from the keyboard and then stores it in a variable. And then we can display that number and then return a 0 to the operating system or the console. Now, I deliberately skipped over the most subtle and potentially confusing element of that program, which is in line 8, the use of this ampersand symbol. So the scanf function takes 2 arguments. The first one is our way of telling the compiler that we want to enter an integer. Don't worry about the specifics of the code. That's just what we'll do. The second thing, this ampersand number, this is a way of telling the compiler, don't pass the number to scanf, because that doesn't make sense. Scanf is going to return a number. So what we actually need to do is pass the address of the variable number in computer memory. And if there's one point of both power, but also subtlety, and also a lot of confusion with the C programming language, it's the use of addresses and pointers, something called pointers. We won't even touch on pointers in this super brief look at C, other than to note they exist. And so what's the real point I'm trying to make here? I'm not really introducing the C language in a systematic way. What I'm doing is pointing out what some of the traps are. And one of them is that because the C language is so tightly coupled to assembly language and the computer hardware, we've got to be really precise about the way in which we pass information around. In this case, we don't want to pass a number to the function scanf. We want to pass the memory location of the variable number in computer memory. So C almost by definition forces you to think about computer hardware when you're writing software. If you're writing embedded systems code, it's exactly what you want. If you're trying to solve high-level problems like RGB to HSL color conversion, or you're trying color space conversion, or you're trying to use the bisection algorithm to solve an engineering problem, C is usually not the best language in which to do that. Here's our second program. We're going to add up a sum of numbers using a loop. Lines 8, 9, and 10 are a for loop. And if you stare at line 8 long enough, you could sort of convince yourself that the for loop starts at 1, continues for while ever I is less than some integer n, and that each time the loop is completed, the I variable is incremented. So this plus plus is C's way of saying increment the variable I is equal to I plus 1. So let's run that code. I've popped the code in questions lectures. We can run it live. Let's take the code, pop it into our window here, and then run it. The program asks us for a positive integer. Let's say it's 6, and it computes a sum. And what that program does, I'll let you to work through the details of how it does it, but what it's aiming to do is add up the integers 1 plus 2 plus 3 plus 4 plus 5 plus 6. If you do that, you get 21. So let's run the program again. Now let's type our positive integer 10. We get a sum of 55. That's the sum of the integers 1 plus 2 plus 3 plus 4 plus 5 up to 10. Let's keep running it again. Let's try a positive number 100, see what happens. That seems to work. What happens if we type in 1,000? What happens if we type in, as our number, 100,000? I'm going to try and get it to break. That doesn't look right to me. If you add up those numbers there, what was that? I think I added 3. That's 100 billion. The sum of the numbers up to 100 billion must surely be more than that. Let's try it again. There we go. So something's gone wrong there. We've added we've entered a large positive number, attempted to add the numbers up to and including that positive number, and got a negative number. Understanding why that has occurred would require us to understand the very hardware specific details of how the C programming language is storing the integer that's capturing the running sum. So I'm not going to go into the details here, but that's the sort of issue that you need to deal with C, where the C compiler is not going to complain, and at runtime, it's not going to do any checking. It's just going to do what you asked. And in this case, add up a whole lot of positive numbers. And because of the particular peculiarities of the way that those integers are stored, you can get a negative number. Doesn't make sense if you've never thought about how computers store numbers before, but C forces you to do that by the nature of the language. Here's our final program that we'll look at, just to give you a taste of what C looks like. This time we're going to compute a base number raised to an exponent. Let's run it again. Let's run it live in our environment. Let's paste that into the window. There's the there's the program. Let me just delete that. Paste the code in. Okay, there's our third and final sample C program. Let's run it. It's going to ask us a base number, 3, an exponent 4. So the program's going to compute 3 to the power 4, and it's going to do that iteratively through this loop that appears in lines 10 to 13. And if you look at it for long enough, you can probably see what's going on. There's a while loop. So while ever this condition is satisfied, while ever exp is not equal to 0, it computes result is equal to result times base. And then this strange instruction here on line 12 is actually minus minus exp. So it's another way of saying decrement exp. Again, are the specifics important? No, in as much as giving you some confidence that if you've only ever seen Python and you find yourself in a course that's going to use C and will introduce C, part of your learning in that course will involve a transition of your knowledge from Python to C. Okay, that's all I want to talk about with C. If you need it, you'll be introduced that language in context. At a superficial level, things like variables, arrays, functions, flow control through for loops and while loops, all that knowledge that you've acquired through your exposure to Python will translate over into C. But there's a whole lot of new stuff in C that you'll be introduced, if you need it, in context that forces you to think about things that Python gently shields you from. Okay. Gear change. We've finished with C. We're going to talk about something called version control. And the way that I'm going to do this is I'm going to give you just a handful of pages of principles, and then Brenton's going to step you through some of the application of those principles so that you can use version control in your own work. Now, for those of you that have really got your teeth into the assignment, you've probably found yourself in a situation where you're working on a large piece of code and you're trying to add a new feature, and you attempt a solution and you realize after a couple of hours work that actually you've only made things worse. And that wouldn't it be good if you could revert to the program that was working yesterday before you spent that couple of hours trying to unsuccessfully add a new feature? So the terminology that a programmer would use is that they want to roll back to an earlier version of the code. You're basically saying, my attempt to add a new feature was unsuccessful. And rather than try and manually backtrack to where you were yesterday when the program worked but didn't have the feature, you'd like to be able to roll back to an earlier version of the code. Now, at the moment, those of you that are working, as I say, on the assignment, you're probably finding yourself to think, oh, how do I reconstruct the version of the code that worked yesterday? It'd be nice to be able to be systematic about that rollback. So that's one aspect of programming that you'd like to be able to address and that we haven't touched on in this course. Another aspect of a programming project that you haven't experienced, at least not directly in this course, is where you have 2 or more people working on the same project. Now you can imagine that requires very careful communication and coordination between those teams of programmers. And it's not uncommon for teams of half a dozen people to be working on the same, or more, to be working on the same piece of code. They may not even be in the same room. They may not even be in the same country. How do you have multiple people working on the same project, on different aspects of the same project, but then have their changes merged into some master code listing? It obviously requires communication. It requires more than communication. It requires some coordination. If you've ever had the experience of working on a Word document with someone where you've got a shared project and someone says, "Oh, here's a snapshot of where my assignment, our joint assignments up to at the moment. How about you work on section 3 and I'll work on section 2?" And you each head off and work on your respective sections as you agreed. You agreed not to touch the other person's section, but you get a situation where you've got 2 documents where you need to take section 2 of one piece of one document and section 3 of another, merge them into a master document and have that as the document that goes forward. Well, if you're talking about small projects, 2 programmers, you're talking about small assignments where you've got a couple of different sections that need to be merged. With a bit of luck, you can do that merge manually. What happens if you've got a software project that's got dozens or more people working on it? There needs to be some sort of systematic way that you can roll back in time to recover code that used to work. There needs to be some systematic way of merging or blending those 2 pieces of software into a master code listing. A system that does that is called a version control system, and it solves both those problems. And the most widely used version control system by far is something known as Git. It's really become the de facto standard for version control systems. It's about 15 years old. For those of you that are into computers and operating systems, Git was started by Linus Torvalds, the person that started the Linux operating system. And he developed Git precisely to enable the coordination and rollback that was needed for developing the Linux operating system kernel. If you're not a computer operating system person, the best way to think about what a version control system like Git is doing is if you think about Wikipedia. If you've ever looked at the revision history in Wikipedia, you can see where different people have made changes to a document, a Wikipedia page. Wikipedia records tracks the history of those changes. So every time an edit is made, it's recorded in the revision history, and that even if that change is later reverted, it's still recorded that change was made. So sometimes you'll get someone that makes a change to a Wikipedia page, and someone, a moderator, will come in and say, "I don't like that change. I want to revert to how the Wikipedia page looked yesterday." It's possible to click a couple of buttons and revert to an earlier version. It's also possible, even if you're not a moderator, to go back in time and look at that Wikipedia page, how it looked yesterday, a week ago, a year ago. What's really happening in Wikipedia is that there's a version of something like Git going on behind the scenes. It's certainly a version control system that's managing that recorded history of changes. For those of you that have a Mac computer and you use is it Time Machine, where it enables you to make backups of your hard disk and say, "Look, something's gone wrong with the computer. I want to recover a file from a week ago." You can actually go back in time and recover that file and look at it how it was a week ago and bring it back to the present time. So that's what version control systems allow you to do, be able to go backwards in time and recover, but also record a history of changes. Now, the Git version control system, as I say, is the standard. I've included 4 terms here that you'll probably see in Brenton's live demo in just a few minutes. They are the absolute bare bones, as far as I'm concerned, terms that are used in Git. Git has a reputation for being powerful and complicated, not unlike C. But the 4 terms that you'll probably hear in Brenton's presentation are, he'll probably talk about a repo, which is an abbreviated form of a repository. The repository is the store of all the different pieces of a project, all the pieces of software that make up all the files that go to make up a project, but also the history of the changes made to those files. So quite a complicated database structure, actually. The next 3 terms, commit, push, and pull, relate to the way in which, if you're working on a project on your computer, a commit makes a snapshot of the project. So it's a point at which can be recovered at some later point in time. A push means that you're uploading a repository that's on your desktop computer or your local computer to a remote repository, probably in the cloud. And a pull means that you're taking the document that's in the cloud and making it locally available to you for further development. So through the course of this semester, Brenton, Sarah, and we've been running a Git repo for the development of the labs and the lectures for this course. Classic example of a case of where we've got a shared project. Each of us has got pieces of the project that we're working on, lectures or labs, but we all want the ability to know where the most up-to-date version of those lectures and labs is up to. So wherever Sarah works, wherever Brenton works, wherever I work is irrelevant. We've got a single source of truth, the repo, which captures all the code that we've written. In this case, it's code, not necessarily Python code, but it's the code that we used to prepare the lectures. And we're able to push our changes to the repository. Other people work on the repository, maybe at the same time on different aspects of the project, and the pull brings them back down for further development. So I suspect what Brenton's going to do is give you a demonstration, a live demonstration of Git, which is, you might think, why introduce it in week 12? Well, actually, I would argue being introduced to version control towards the end of your first semester of study is a great time to introduce it, because Git works well beyond any computer programming language. It also works for file storage that you can use as students. So it'd be a great habit for you to get into as a way of backing up your assignments and your documents and being able to recover them from earlier points in time. At this point, I'm going to hand over to Brenton. We'll probably take a little moment to do our handover of Zoom, but I think Brenton should be online and able to do a live practical demonstration. Let me see what I need to do.
Yep, I'm here. I think if I click share screen, it might just take over. What, did you still there, Steve?
I am.
Oh, sorry. Yeah, your video paused. Yeah, I'll just click
okay.
Share screen.
Give it a go.
Select the right screen.
You're in control. I'm out.
Alrighty. Thanks for that, Steve. Okay. So yeah, I'm going to be going over some of the more practical aspects of how to use Git and what it can do. I'll be showing you how to do Git in PyCharm, just because PyCharm is at least an environment we've used before, and it also has some nice features like it will apparently install Git for you. If you haven't got it installed, you don't have to go and find a Git client and so forth. But what I might just show you first, just as a bit of a motivator, this is my GitHub page. So just taking a step back, the Git system is a piece of software which keeps track of all your code and allows multiple people to use it and so forth, all that stuff that Steve was referring to. GitHub is basically cloud storage that does cloud storage using the Git software. So, you might have Dropbox that uses Dropbox's proprietary algorithm, proprietary software and so forth for doing cloud storage, or you might have Google Drive that does it. Well, GitHub is basically cloud storage that has Git underneath. Now, if we go and find one of the repos that I've been working on, let's find one where I know there's a lot of history. Let's have a look at the history for the assignment. So this ENGG1003 private repo is where I have all we all, Steve, I, and Sarah, we all contribute to this. We have the stuff that we wouldn't necessarily want to be public. It's like the assignments and the exams and the quiz and all that sort of draft stuff. But here's the section of the repository that has assignment 2. And if I go to the assignment2.txt file, this is basically the source code for the PDF. This is a language called LaTeX, which a lot of you will hopefully get exposure to before or during the writing of your final year projects. Try not to do that in Word. There too, that LaTeX is a great system for that. But this is the current version of what the code looks like. And we can click this history button here. And this is all of the comments, all of the snapshots in time that have been taken for this document. So if someone, if, for example, we want to know what this document looked like a couple of weeks ago, we can click one of these. This is like a hexadecimal hash. It's sort of like just a unique identifier for each of these comments. If you click that, you can see what's changed. The stuff in green is what's changed. The stuff in red is what's been removed. And the stuff in white is just there for some context so you can find where in the file stuff has changed. This is what's called a diff output. There's a standard Unix and Linux command called diff that will produce this sort of thing if you try to find the difference between two files. So the full history of the files there, I can see exactly what's changed in every file in this repo since it was made, like at every comment. And as Steve was saying, it's fantastic if you want to take some working code, take a snapshot, then go off and experiment with it, knowing that you can roll back to something that works if you need to. Anyway, that's just a little bit of motivation. This is what Git looks like in GitHub. In order to do the demonstration, repeat the demonstration that I'm about to show you, you will have to make your own account at GitHub. It's going to show you how to connect PyCharm to a GitHub repository. So if you go to GitHub and click sign up, I'll leave you to work that out. I'm not going to demonstrate it because I don't have an email address that has not been used for GitHub before. I haven't gone and created a new email address just for the sake of that. Hopefully you've done enough signing up of online services that you can work out how to create your own GitHub account. Okay, so we're going to be doing two things. If we want PyCharm to connect to a GitHub repository, we need to both configure PyCharm to do that and also create the repository in GitHub. So we'll have this so we can view both of them at the same time. Where is the new repository button? Here we go. I'll create a new repository just for the sake of this demonstration. So I'll make it a public repository so everyone can go and look at what I've done. We can give you the link in the Discord server somewhere. And I'm just going to leave all this as defaults. Now, after you create a Git repository, it gives you this page, which gives you a whole stack of seemingly cryptic commands to run. For the time being, we're going to ignore all this and just let PyCharm fix this up as needed. If you're quite an advanced Git user, perhaps you'd prefer to use the command line. A lot of experienced programmers do prefer command lines over GUIs because it's faster when you know what you're doing. And if you don't know what you're doing, it's impossible. So anyway, the main thing we just want is this link here. I'm going to click, make sure that HTTPS here is selected and you want this address. We'll come back to this later. Let's go to PyCharm and just pretend we're creating a new project. Make sure we've got Python 3. Okay. Starting from scratch. We've got our brand new Python project. We'll go and do stuff to this in a second. And we want to make sure this Python project is in our brand new Git repository. What do we do? Well, first thing in PyCharm is we go to this VCS menu here. VCS stands for version control. I don't know what the S stands for. It calls it version control integration. We'll just call it that. So we'll click that, and then this window appears, and we need to make sure that we're selecting Git. So Mercurial and Subversion are both just other version control systems. We'll use Git, and it goes and does a bunch of stuff in the background. What it's done is enabled Git or created a Git repository in the folder that their project is stored in. And you'll see down here, it says created Git repository, it gives you the folder there. And you'll see that main.py is now in red. We'll come back to that in a second. Let's say we now want to do what's called a commit and then a push. So a commit would be taking a snapshot of the state of this project. Somewhere, where are we? I forgot where add file was. Git add. Okay, so Git will only keep track of files that you have explicitly added to the Git repository. By default, it doesn't go and add everything. A lot of projects might have a lot of temporary files or a lot of like gigabytes of data files or whatever that you don't want to keep track of. And so by default, you need to manually add files to the Git tracking. So we'll go to main.py. I right-clicked on that, went to Git and pressed add. When you're used to this, you'd use the Control-Alt-A shortcut. That would be a lot faster. I'm just showing where to find it manually. We'll add that. You'll see it now turns green. That tells you that it's been added, as opposed to red, which is sort of like an untracked file or a file that's had changes that haven't yet been added. And down here, this little pop-up here says project configuration files can be added to Git. That's everything in the virtual environment folder, I believe. I'm not going to add them. Maybe you want to, maybe you don't. I'm only going to keep track of the PI file for the sake of this demonstration. So we've added, right-click, Git, added that file to our repo. It's turned green. Now we'll go and do a commit. So a commit takes our snapshot, and this window here appears. Down the bottom, it's got a list, sort of a preview of what's changed since the previous commit. There's not been any previous comments, so everything has changed in this file. And we've got an opportunity here to type a thing called a commit message. I'm just going to call this the initial commit, just for want of something better. Comment messages this is just the log of all the comment messages for the ENGG1003 repository, where all the lecture notes and so forth are published. Typically, you try to add a message that's reasonably descriptive. If we scroll down far enough, obviously, sometimes I just get frustrated and don't care. there's the XKCD comic reference. And as you can see, there's been a lot of these. So well, there's a few more ASDFs in there somewhere, But this is all the comment messages going back to 2019. Everything's still there in the history somewhere. But you try and make something a bit descriptive. All these ones with that are very well labeled. There's Steve's, I dare say, because he's working on the lecture notes, and he's also a lot better at documenting stuff than I am. I'm a bit lazy. Anyway, there'd be ways to work out who did what in Git as well, but that's a bit beyond things. Anyway, let's do our initial commit. We'll click commit. So now there's a snapshot of what the project looks like at this point in time, but we have not put these changes onto our Git repository yet. If you've been paying attention, you'll realize that PyCharm has no idea that the Git repo on the right exists yet. The first time you do a push, so firstly, a push is when you take all of the changes that you've made to your Git repository, all the changes you've made to your project, and copy them to a different computer, basically. So we're pushing the changes that we've made to our cloud storage. In this case, we're going to configure it for our GitHub cloud storage. This window pops up, and it's basically saying, I have no idea where you want me to store these changes. We haven't specified it yet. You need to click this little link here that says define remote, as in we're defining where the remote storage is, where the remote repository is. The fact that it's got origin here, that's just a standard name for sort of like the top level Git thing. It's complicated. We're not going to go into that. Everything's just going to be origin master in this sort of like, Git has this idea of things called branches, where you could have different versions of the code at the same point in time. It can get really complicated. We're ignoring that. Just leave the name as origin and copy this HTTPS address into the URL. This is now the location of our remote Git repository. Click OK, and then click push, and it's going to ask me, hopefully, to log into GitHub. Nuts. I've done this before and it didn't ask me to log into GitHub. Hang on a second. Let's do that again. but I'm going to just delete delete the fact that it knows about GitHub. Where on earth? GitHub. Let's just delete that user. Okay. I'm going to make some changes to that code, and there's just do a an add, then a comment. You'll see down here, I've taken some changes since the previous comment, and it tells me exactly what those changes are. You know, line 18 has been added. And I'm just doing this again so that I can show you what it looks like when you have not logged into GitHub yet. So I'm doing an add, a comment, then a push again. And hopefully this time it says, oh, I have not logged into GitHub. This is what you're going to see the first time. You're only going to see this the first time you do it. We'll log in via GitHub. It will bring up a browser window. And in this browser window, you do your GitHub login. So we'll authorize for PyCharm to have access to GitHub. Hopefully it's going to ask for my username and password. It might not, because it's probably been stored in this browser, actually. Come on. You're taking long enough that you're getting me worried. Please tell me my internet still works. Yeah, cool. My internet's still working. The joys of Australian broadband. All right. Oh, come on. Let's just try this again. Yeah, push failed. It doesn't know who we are. Push, push. Log into GitHub. Oh dear. Well, at least you've seen it working. While that's thinking, I'm going to show you what our Git repo looks like now, because two of those pushes did actually work. Well, sorry, one of them did actually work. It just didn't bring up the login to GitHub window because I'd already done it. If we go to just your main GitHub page and search for your repositories, no, I'm not answering your question now, I'm lecturing. You can see that the Git repository that I made is in our GitHub account. We'll click that and we can see that main.py is there. It's the file that we added to the repo and then pushed. And there it is. So we now have a cloud storage copy of our file. If you want to view this, I'm going to copy and paste that into the lectures channel. You can hopefully see that. Let's just double check we can see that in the private window. Yep, you'll be able to see that. Then if you click history, you'll be able to see the full history of the file. Now there's only one comment because the other one hasn't worked yet. Thank you, Firefox. Let's going to try doing this in a different window. Yeah, it seems that their authorization server's gone and died. Anyway. Anyway, the file's now there. If this authorization did eventually finish and we did another push, you'd be able to see that that ASDF comment appear in the current version and in the history. And that's kind of all there is to it. The process, assuming their authentication server comes to life again, the process is to do some code. You go and let's get rid of this logging in window so I get keyboard focus back. You go and you do your coding. Control-Alt-A to add. Whoops, that's settings. Where are we? You do some code. You add the file. You do a comment. You type in the comment message. Why is that not letting me? There we go. Do your comment message, and then do a push. And at this point, you see it's trying to commit. It's trying to push both of these commits because they haven't worked yet. Hey, there we go. It worked. It worked when it wasn't being screen shared. It worked when it wasn't being screen shared. Oh dear. Okay. third time lucky. You'll see that this authorization now worked. And down here in PyCharm, it says push 2 comments to origin master. If we now go back to our GitHub repository, you'll see that this text here is the commit message, like the most recent commit message. If we now click, I'm not going to click, if you click the comment message, it goes and shows you the changes that were made. But if we just click the file, there's the most recent version of the file. You can see that on GitHub. If you hit F5, if you're playing along at home, you can hit F5 and see that this garbage is now in the file and it matches what's in PyCharm. And if we click history, you can see those 3 comments have now made it to GitHub because the authentication server finally decided to come back to life. And you can click the comment hash on these things and see what changed. And that's basically the guts of it. This is sort of the fundamental usage of Git, is taking comment snapshots so that you've got something to roll back to if you need it. You can go and see what changes you've made. If something breaks and then you don't know what changed and you need to do a comparison between something that you know works and something that you've got now, Git will let you do it. If you actually want an older version, let's say we want to roll all the way back to our initial commit. Let's see if I can work out how to do this. This might be a complete disaster. Normally you do a thing called checkout. Compare with revision. Here we go. If we want to know what's changed since the very first version, that's a left and right and A to B comparison showing you everything that's changed. So if you know that this version worked and this version didn't, I'll just find that again. So it's git current file. Oh dear, the window's open. No? Git current file, compare. So show diff will show you all the differences made since the last commit. And compare with revision allows you to choose an arbitrary point in time that you want to compare to. So if we know that this version, the initial comment worked and the current version didn't, what changed? Well, it's probably because we've introduced a stack of syntax errors. But this window here gives you an A to B comparison, so you can see, hopefully quite easily, what has changed. You just scroll down and look for all the green and red stuff and see, try to work out where you've introduced an error that would break your code's behavior. Anyway, I think that's the guts of it. Is there anything else you wanted me to add there, Steve? Anything you can think of?
No, absolutely not. That's beaut, Brenton. No, I think you touched on all the 4 points that I mentioned in my closing slide, which was a repo, a commit, and a pull and a push. That to me are the fundamentals, and you've stepped them through in practice.
Yeah, well, I guess the only other thing to add is that Git as a system doesn't care what data types you're giving it. So you could have your assignment 2, you can create a Git repo for your assignment 2, and you can include all the PNG and TIFF and JPEG files. You know, Git will keep track of versioning of arbitrary data. You can use it for your lecture notes. You can use it for Word documents. You can use it for whatever. The only file types that Git has an advantage for is text-based file types. If you want to track versions on a Word document, they're predominantly a binary data type, and you're not going to be able to see differences in a Word document because it's going to show you differences in the raw file on the disk, not differences in the actual text in your Word file. Oh, yes, Sarah's just noted we haven't done a pull. We haven't done a pull. Okay, let's... Good question. Let's demonstrate a pull.
Delete your local version and.
Yeah, let's. Oh, I don't know how to do that yet. So we'll do it live. Where are we? Close project. Okay. I haven't done this. I haven't read the docs, so we'll work it out. I'm going to take a guess that this get from VCS button is going to allow us to download something from Git. So let's download something different. What's this? Factor test. This is a little bit of C code. but we'll load it into PyCharm just for the sake of demonstration. What happens if someone gives you a URL to a Git project and you want to load it into PyCharm? In GitHub, this code button here allows you to download code. You can download it via SSH, which is, if you know what it is, you probably don't need me to explain it. If you don't know what it is, just click HTTPS. Well, I don't have time to teach you how SSH works. It's fantastic, but anyway, we'll copy this URL. You can also download a zip and then manually stuff around with it. But we'll copy that URL there, click clone, and cross our fingers. And there we have it. We have some C code in PyCharm, which is obviously not going to work because it's
slightly disturbing, but it worked.
Yeah, so that's all you have to do to open projects in PyCharm. I think maybe this is a lesson for us, Steve, for next year. We just distribute templates in Git because giving people a URL to something we can keep track of. If you've been playing along with the assignment to test code, that would have been much better to distribute via Git, because every time I make a change, I then need to upload a new copy to Blackboard, and you've got to download a new copy and the file name changes and all the rest of it. It would be so much simpler if we gave you a template and you just downloaded the most recent version on Git. It's just a much better way of distributing files. Only issue is that GitHub is blocked in China. So if you're a student in China, maybe we'd need to make some special provisions for that. But for the most part, Git is a much better way of distributing code than Blackboard. So anyway, that's how you do a pull. You get someone to give you the URL to a project, or you manually find a project, and then you get the URL out of Git. Or if you want to give someone else a project, that's the URL, you email them, and then they can do that. Like I can go to the command line here, and do a thing called a clone of a repo, and we've now got that code sitting on my hard drive by doing a single command. Things are very quick on the command line. If you ever want to push through the pain of learning how to use a command line, I strongly recommend it. Other people might have different opinions, but you know, that's how you do a clone on the command line, or a pull. Oh, sorry, yes, the difference between a clone and a pull. I've just started introducing new terminology without explaining it. A pull will give you the most recent version of a Git repo that you've already got a copy of. A clone will download a brand new one from scratch, which is why I use the clone command there.
So then you could take that clone and then roll back to how it looked a week ago.
Yeah. So now that I've got a clone of the Git repo, I can look at all of the comments that have been made in the past. There's only 4 of them. This was a simple one that I created in 2019, back when we all had to learn C. If you're doing a pull, it's probably because you're sharing code with someone else, or you're sharing code between different computers. So the main thing I use Git for is translating lecture note material, that, you know, coursework material that I'm writing between my desktop at home, my laptop, and my machine in my office at uni. I use Git as cloud storage because it's just a lot more powerful than just using Dropbox or OneDrive. You know, those cloud services tend not to give you version tracking and so forth. They give you the convenience of, you know, automatic updates and so forth, but Git gives you more control and a lot more features. So cool. I think that's the guts of it that we wanted to demonstrate.
Absolutely. Wonderful. Thanks, Brenton. That's great.
Back over to you, Steve.
Super. Thanks very much. Look, and thanks everyone. And thanks so much, Brenton, for that live demo. You did things there that I certainly can't do. Certainly. So that brings today's Monday, week 12 lecture to a conclusion. On Thursday, I'm going to structure Thursday's lecture around the upcoming final exam. And so I'm going to give you as much detail as I reasonably can about expectations, the way that you'll do the exam, how the exam will look, how it'll run, how it'll be assessed and such. That is the sole topic of Thursday's lecture, and that'll be at 4 p.m. So until we catch up on Thursday, I'll say bye for now.